Now let's do Roadrunner's problem, part 1. Naturalists placed 30 roadrunners in a game preserve that formerly had no roadrunners. Over the years, the population grows as shown in the table and in figure 8-3L. So the number of years 0, there are 30 roadrunners in a preserve, meaning they are being preserved in some place. Okay? So after 1 year, there are already 44 road runners, so congratulations. After 2 years, there are 58 road runners until the 11th year, wherein there are already 293 road runners. So you can see an increasing trend in the number of road runners as relative to the number of years that have passed. So making a scatter plot of the data where, let me just clarify this. This is years, and this is 5, 10, 15, and this is 100. These are the number of road runners, 200, 300, okay? And these are the number of road runners. And the x here is the number of years. Okay. Now the plot is something like this. So we have, of course, from 0 years, there are already 30 row runners. So we have a y-intercept there. Okay. Now as time goes by, it seems like it is exponential in nature. Okay. This one will never reach the x-axis because initially you already have the number of road runners. So this is like an exponential growth, right? But let us take a look. For question letter A, give a physical reason and a graphical reason why a logistic function would be a reasonable mathematical model for the roadrunner population as a function of time. By logistic regression, find the particular equation of the best fitting logistic function. Plot the graph and the data on the same screen. Use a window with an x range of 0 to 20 years. Sketch the result. Okay, so what is the most, what do you call this, the most complacent way to explain why a physical reason and a graphical reason? Okay, physical reason is that, all growth have their limits, right? So, for example, let's just make the growth of a person as a logistic function. Now, there are certain times when the growth of a person from being a baby growing to an adult, there is a time when the, what do you call this, the growth is exponential, especially when they are, when people are reaching the teenage years or the adolescent period, wherein growth is really exponential. But up to a certain age, height versus age, this, what do you call this, the growth of the person has to level off. It won't reach infinity, right? Because if it reaches infinity, then we would not stop growing and the cells would not stop dividing. That's one comparison between a physical reason for the growth of a person as compared to a growth in general. So in this case, we're dealing with road runners in a certain preserve, in a certain location, a strategic location, for example. But over the course of years, you would notice that the population of these road runners will eventually level off. Why? Because first of all, that preserve has a certain limit, and that preserve will eventually, what do you call this, have to accommodate only a certain population of road runners, because otherwise there would be scarcity in, for example, food and the habitat. Okay, so uh, for a course of, let's say, 20 years, their population will eventually level off. Okay, so the general explanation of this is that growth is exponential, but physical limits make the population level off. So a logistic function fits the data because they have asymptotes in both the endpoints, but are not exponential in the middle. Remember the logistic function, the logistic graph? It's something like this, right? It has the characteristics of an exponential function, but in the middle it inflects, or there is a point of inflection wherein there are asymptotes, the upper bound and the lower bound. Okay? So the same is true for the population of the road runners. So eventually the population growth will inflect, it will have an inflection, point of inflection, and it will eventually level off to a certain limit. Okay? So plot the graph and the data on the same screen. Use a window with an X range of 0 to 20 years. So we'll use the graph, of course, the logistic regression. And by logistic regression, we are going to get this logistic function y hat is equal to 327.5140 over 1 plus 10.0703 e raised to negative 0.4029 x. And if we are going to plot the graph of the data on the same screen, then we will get the same the same plot as this one. So using the grapher, we could get this plot here. Okay? So remember, our logistic regression is this. Okay, so let's go ahead. So what does your mathematical model predict for the roadrunner population at x is equal to 20 years? What does the model predict for the maximum sustainable population? At approximately what value of x is the point of inflection where the rate of growth is maximum? So we're going to answer one by one. What does your mathematical model predict for the roadrunner population at x equals 20? Of course, we are going to use our model. And what is that? Y hat equals 327.5140 over 1 plus 10.0703 e negative 0.4029. So using x equals 20, how do we get this? Just substitute x here, and that will give you y hat was 327.5140 over 1 plus 10.0703 e negative 0.4029, and your x is 20. Okay, you cannot see the other letters, so let me rewrite it here. Y hat of 20, okay, is 327.5140 over 1 plus 10.0703 e negative 0.4029 20, and using a scientific calculator or your grapher, this will eventually give us. So if we're going to replace our x with 20, that's 327.5140 over 1 plus 10.0703. Yeah, where is e? Okay, shift E, and negative 0.4029 times 20. This will give us 326.473, or this is approximately 326, okay, road runners, right? So the answer for this, the population of the road runner at 20, so y hat of 20 using our model is approximately 326. Okay? So this is the population of the road runners after 20 years. What does the model predict for the maximum sustainable population? So this is A, and for B, okay, using again the model, let's take a look at the model. Y hat is equal to 327.5140 over 1 plus 10.0703 e raised to negative of 0.4029 x. So if x is very large, if x approaches infinity, or if it's very large, then what would happen to our e? That would just be, this will be 300, okay, y equals, or y hat at x is very large, so say infinity, so 327.5140 over 1 plus 10.0703 e negative infinity, meaning it's going down. So if e is very large and this is 10 is very small, so actually we could write it like this, divided by e raised to infinity. So if this is very large and this is very small, so this could be taken as 0. Am I correct? That's why your y of x is very large would only be 327.5140, or this is approximately the maximum allowable population of the road runners that the preserve could sustain is 328 road runners, right? Okay. So that is for question number 2. At approximately what value of x is the point of inflection where the rate of population growth is maximum? Okay, so how do we get the point of inflection? Remember in logistic function that to get the point of inflection we have to get the asymptotes, right? And our asymptotes, so this is letter C for this question B, okay? Or let's call them, this is 1B, so this is 1B, 2B, 3B. The point of inflection occurs at the midpoint of the limits, the asymptotes. So our asymptotes here are y hat equals 0, right? And y hat is equal to 328. That's the maximum allowable population of the, what do you call this? The, what do you call this? The road runners. Okay, so the point of inflection, POI, would then be equal to the midpoint of these asymptotes. So we have 328 divided by 2. So that would be 328 divided by 2 is 328 divided by 2. So that would be 164. Okay, that's the value of our point of inflection. So at y equals 164, so 164, we are going to use the equation of what I call this equation of the logistic regression. So 164 is the y hat is equal to 327.5140 over 1 plus 10.0703 e raised to negative 0.4029x. And arranging this entire equation will give us, so this will give us 1 plus 10.0703 e negative 0.4029x is equal to 327.5140 over 164. And 10.0703 e negative 0.4029x will give us 327.5140 divided by 164 is equal to 1.997 minus 1, so that's 0.997, and 10.0703 e raised to negative 0.4029x, and that should give us e negative 0.4029x is equal to 0.997 divided by 10.0703 will give us 0.099007. And this is the natural logarithm for 4029x is equal to ln of 0.099007. So this will be this is a property of the natural logarithm. So negative 0.4029 x is equal to ln of 0.099007, and our x is there 4. So that will be divided by negative 0.4029. This is approximately 5.739 years. Okay, so the point of inflection occurs at x is equal to approximately 5.7 years. Okay? Now if you got 5.5 years, it's okay, because what we did here is, we actually rounded the number of road runners at y is equal to, or as x approaches very large numbers, it's 320 road runners, but actually you could round it off to like 327.6. Okay, so or 328. Let's say the asymptote is 328. So anyway, you will have to get this x is equal to 5.7 years as the point of inflection. Okay, so letter C. Find the mean y, the average of the y values. Use the mean to calculate S's def, the sum of the squares of the deviations. Using the regression function in part A, calculate S's res. the sum of these squares of the residuals. Then find the coefficient of determination. How does this coefficient show that logistic function fits the points quite well? Okay, so we would need to have a table, but I already prepared the table here, and also the SSDev and the SSRes. So it's up for you to follow. So our mean is 158.5 roadrunners. How did I get the mean? Where is our table? This is our table. Okay, to get the mean for y, just add all of the. So let me just erase all of these things. Okay, to get the mean for the y, what you need to do is to get a summation of all these numbers of y divided by n. And our n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the sum of these y values here is 30 plus 44 plus 58 plus 81 plus 110 plus 138 plus 175 plus 203 plus 234 plus 260 plus 276 plus 293. So the summation is 1902, and divided by 12, the mean should give you 1902 divided by 12. That will give us 158.2. Now let's see if the mean matches what we got. So 158.5, and in here we got 158.2. Maybe there's something wrong. So we're going to do it again. We have 1902 divided by 12. 1902 divided by 12. That gives us 158.5. Yes. It's 158.5. Okay, now we have the same mean. So using this mean, we will get, okay, let's get the entire table. Okay, so now I have the table for my road runners. So the mean here is 158.5 road runners. Okay, I'm sorry for that. $158.5 road runners. So y minus y, or y minus the mean, that means the deviation from the mean. So we have negative 128.5, negative 114.5, negative 100.5, negative 77.5. That's just subtracting your y from, you're subtracting your mean, from the y value. That's why it yields negative here. Okay, so 30 minus 158.5 will give you negative 128.5, and so on and so forth. So these are our tabular illustrations for the deviation from the mean. Now the squares of the deviation from the mean would be this. So just square this. It will be positive, so 16,512.25. Go down until 134.5 square. That's 18,090.25. Now we will have y minus y hat. And what is our y hat again? Our y hat is equal to 327.5140 over 1 plus 10.0703 e negative 0.4029 x. So as you know, this is a little bit of lengthy. The computations like statistics. Okay, you have to compute for all of this, and that's the way to do it. Okay, so we could, I mean, we cannot complain about it because in the end we're going to do it anyway. So I mean, it takes practice and hard work to finally be able to compute for the sum of the squares of the deviations and the sum of the squares of the residuals. So anyway, y minus y hat, just what do you need to do here is to replace your x here with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 to get your y hat for each of the x's, and then subtract it from your y. Then you will get this, and so on until here. And you square this is called the residual, okay? This is the deviation, and this is the residual. So if you square the residuals, these are the squares, okay? And if you get the sum of the residual, of the squares of the residuals, this would be the sum of the squares of the residuals. This is the sum of the squares of the deviations. And then finally getting the coefficient of determination, r square, s is dev minus s is res, over ss dev. So that gives us 0.9997, which is the r square, and it is very close to 1, right? Now to get the correlation coefficient, r is equal to the r square, and our r square is very, very close to 1, so 0.9997 will give us a coefficient of determination, or yeah, correlation coefficient rather, of 0.9998, which is very, very close to 1. And indeed, if r is positive 1 or negative 1, positive 1 if the data is increasing from the original point up to the succeeding points, and if r is negative 1, then it is the y's are decreasing from original x to the succeeding x's. So if the r is very close to 1 or negative 1, then it has a very strong correlation. And therefore, this shows that the logistic function fits the points quite well, right? So therefore, we could take the logistic regression function as the proper function for this data, okay? The population growth of the roadrunner. So that's it for regression for nonlinear data. I hope you were enlightened about the complexity of this lesson, and it takes a toll and hard work and of course patience to solve for statistical like analysis here. So just with patience and virtue, you could succeed in this lesson of the chapter, and of course with a little help of constant practicing. Okay, so again, thank you for watching. Have a nice day.